Okay. So today I thought I would talk about linear regression or best fit lines. I didn't get a chance to look at what was gone over in lecture yesterday. So if there is something about orthogonal matrices or symmetric matrices, I think I'm going to postpone that to Monday to go over that. Or maybe if there's time after, we can go over it today. But for now, let's focus on best fit lines. So there is a warm-up question that I have. A warm-up question, just to get everyone on the same page, which is true, false. So everyone can think about this. If you have a basis, if W is a subspace with basis x1 through xp and v1 through vp is another basis of W that is also orthogonal, then v1 through vp was gotten from x1 through xp by Gram-Schmidt. So everyone think about this for about 30 seconds. Okay, what do people think? True, false? All right, so if you have a basis of W, x1 through xp, and then v1 through vp is some other orthogonal basis, then is it true that v1 through vp was just gotten from x1 through xp by Gram-Schmidt? If you perform Gram-Schmidt on the first basis, do you get the second one? That is false. Right? Just because v1 through vp is orthogonal doesn't mean it was gotten from x1 through xp. Right? So, right, if you have, I mean, there are many orthogonal bases of a space. And so if you do Gram-Schmidt on x1 through xp, you don't necessarily get v1 through vp. In fact, remember, if you do Gram-Schmidt on x1 through xp, it actually depends on the order you choose. If you have two vectors like this, say this is x1 and x2, if you do Gram-Schmidt, where you do x1 and if you pick the order x1, x2, you're going to get something like an orthogonal basis like this. If you do x1 first, then x2, what I mean by that is you perform Gram-Schmidt on the ordered basis x1, x2, but you could also do Gram-Schmidt, this is a G, Gram-Schmidt, on, if you switch the order, then x2 is going to stay the same, and you're going to get x1 that's orthogonal to x2, and so this will be your basis. And these two are different orthogonal bases. So Gram-Schmidt, depending on the order, can give you very different things, and orthogonal bases can just be very different. So it's not true that you get a unique orthogonal basis from just a basis. You need to pick an order. Okay, hopefully everyone's question from the quiz. Was this a question on the quiz? I don't think it was. Oh, you have a question from the quiz. Okay, yeah, we can, yeah, do people have questions? We can field some questions now, and then we'll talk about best fit lines. So maybe if people have any questions. So the question is, for any vector in Rn, the set of vectors A with proj onto the span of, okay, so this is a question. Let me write this down then. Okay, this is a question from the quiz. It was this question on the quiz that was the set of vectors whose proj is 0 forms a subspace. Yeah, this is just a fancy, this is a fancy way to say, or maybe a convoluted way to say the orthogonal complement of a space. So let me write that. For any B in Rn, this, I was writing in set notation, the set of vectors A such that the projection of A onto the span of B equals 0. This set of vectors is a subspace. This is true, false. This is exactly the orthogonal projection. So here I'll draw B. Here's B. So the span of B is just a line, right? And so you're saying the set of vectors whose projection onto this is 0. What that means is that A is exactly orthogonal to B, right? If the projection is 0, it means that A has to be orthogonal to B. And so this is actually, this is equal to the span of B orthogonal complement. So it is a subspace. Yeah. If you couldn't picture this, I mean, you can just check at the subspace by checking all 3 conditions. You could check, is 0 in it? Let's call this subspace H, maybe. Is 0 in H? Yeah, the projection of 0 into something is 0. If you have A, maybe U plus V, sorry. U and V are in H. Does this imply U plus V is in H? And yeah, just the projection is linear. The projection of U plus V separates into the projection of U plus the projection of V. And CU and H, this imply, sorry. If U is in H, this implies CU is in H. And yeah, for the same reason. So yeah, this is true. Okay, I'll let you think about that for a little bit. Is H a plane? It is so B, if you're an Rn, it depends what you mean by plane. If you mean plane is 2-dimensional, then not necessarily. Since B is 1-dimensional, the orthogonal complement, this is 1-dimensional, the orthogonal complement will be n minus 1-dimensional. So this is going to be n minus 1-dimensional. Let's close under addition. Yeah, so let me draw, in R3, if B was, this is an R3 now, then W perp is going to be a plane. But if you're in R7, then this is W perp. Then W perp would be like 6-dimensional. Y is closed under addition. So why is this true? So it's both of these are true just because the projection is a linear transformation. So what I mean by that is the projection of U plus V onto a space, I'll just do this one for now, is equal to projection of U plus the projection of V. Just because dot products are linear. So if we just complete each side with its formula, you get U plus V dot B over B dot B, B. Here's U dot B And here's v dot b. All right, and so now is this true? And it is, because just the dot product is linear. U plus v dot b equals u dot b plus v dot b. And it's the same reason. The same reason is why 3 is true. It's closed under scalar multiplication because the dot product is linear under scalar multiplication as well. Okay, great. So let's talk about best fit lines. I'm going to go to the next page. Okay. Okay, so this is, a real world application of orthogonal projections. This is used all the time. This is the basis of linear regression, which is really the heart of a lot of things that might sound scary, like machine learning, for example, or data science. Linear regression is used all the time, and we're going to go over how it works. And so the setup is, the setup is you have some data points, x1, y1, xn, yn. So maybe you collected the data points x1 through xn, and their outputs y1 through yn in some lab or whatever, and now you have some points, and you want to find a line that is best in some way. Okay, and so how do you do that? Right? And so this is say, typically you're given in the real world, typically you're not given two-dimensional data points. You're given stuff like x11, x12. You're given a huge vector and an output, or maybe several outputs. And so it's really high dimensional data because you have a lot of factors maybe you're considering. So it's high dimensional. But that's harder to visualize, even though the theory is still the same. So we're going to do two-dimensional data points. Okay. So how do we find the best fit line? So what we want is to find a line. In this case, since it's two-dimensional, a slope and an intercept such that, so we want all of these points to fit on this line. So y1 equals mx1 plus b, and y2 equals the same mx2 plus the same b, and so forth. Right, and we're just gonna, like always, we're gonna write this in a matrix form. So this is the y vector equals, so m and b are our things we're solving for. If we multiply this out, m is being multiplied by your x vector, and b is just being multiplied by 1 each time, so we're just going to put some 1s in here. And now we have a matrix equation. This is y equals a times m b. Okay, and we want to find m and b that satisfies this linear system, but actually there's a problem, which is that this linear system is not consistent. Or it's usually not consistent, which is to say that there is no line that goes through every single data point. Sometimes your data points just don't fit on a line, and so this is not consistent. And so what you want to do, though, is you want to find the best line possible that could do that, which is to say that you want to find a line that's, this y, so saying this linear system is not consistent is saying that y is not in column space of A, And so we can try to find m and b such that a times mb is the closest point possible to y. So what we're saying is we want to find m and b such that a times mb is equal to the orthogonal projection. I'm going to go to the next page. So instead, we want to find mb such that a times mb equals not y, but the orthogonal projection. Because this will be consistent. Because this is in the column space of I. So a drawing is you have your column space. You have y sitting out here, and we're finding the orthogonal projection. So we're finding, so this is the orthogonal projection. And we want to find MB. So actually, we're not technically finding this orthogonal projection. There's a question, which is why is A with the right column all ones? That's just because that's how we transform this linear system into a matrix equation. Right, so if you just multiply out the first row, you get, if you look at the first row in this matrix equation, you get y1 equals m times x1 plus 1 times b. That's exactly this equation. Here's okay, so we say MB is that satisfies this equation is called a least squares solution. So let's parse this definition. This is a common mistake people make, which is the least squares solution of a linear system ax equals b is not the projection, right? This not the least squares solution. Right? The least squares solution is this MB. Right? It's this vector that when you multiply by A gives you the orthogonal projection. Right? So there's a little difference because, like, for example, they're kind of just in different spaces altogether. Right? The column space of A is living in some space, and MB over here is living in some entirely different space. Here's MB. And A takes this space, this is the input space. This is the output space. And A maps vectors in the input to the output. And so this orthogonal projection is kind of in just a completely different, it's in the codomain of the matrix transformation. MB, the least squares solution, is in the domain. So they're just lying in different spaces. And another thing that we're gonna stress, so that's kind of one thing to stress. The other thing is that we really have a least squares solution, which is that the other thing people often forget is that the least squares solution is not unique. Why is it not unique? Well, we're solving a linear system here. And so when do linear systems not have unique solutions? they have unique solutions if and only if there's a pivot in every column, which is to say yeah, it's unique if there's a pivot in every column. It's not unique if the columns are linearly dependent. So unique if and only if the columns of A are linearly independent, which is not always true. So just another thing to note. Okay, so this is exactly how you find least square solutions. One way to do it is you have y is given. You have a is given. So you can project onto the column space of A, we know how to do that. And then you can solve this linear system. But that takes a couple steps, right? Because to project on the column space of A, to do this, you need an orthogonal basis of the column space of A. So, a priori, to solve this, you need to first perform Gram-Schmidt on the columns of A. That gives you an orthogonal basis. Then you need to project Y onto it. And then you need to solve a linear system. And those are a lot of steps. And so actually, there's an easier way to do this, which is you solve what are called the normal equations. Okay, and so we'll just go over that briefly, and then we'll do an example. So instead, to find the least square solutions, we solve what are called normal equations. And the normal equations are, well, we use two facts. First fact is that y minus the orthogonal projection onto the column space of a matrix, or just y minus the orthogonal projection to anything, should be orthogonal to column space of A. Right, so this is something we've talked about before. This vector, which is green, is orthogonal. I'm just drawing the exact same drawing I just drew. This green vector is orthogonal to the column space of A. And the other fact we're going to use is that the orthogonal complement of the column space of a matrix is equal to the null space of the matrix transpose. This is something we talked about last section. And so putting them all together, we get that this vector is in the null space of A transpose. A transpose times this vector equals 0, which is to say that I guess the 0 thing we're using is that A times MB equals projection of A. So plugging it in, we get what are called the normal equations. And so this is how you solve for least square solutions. You just solve a single linear system, which is this linear system. You're given y, you're given a, you can calculate everything here, and you solve for m and b. So let's do an example. I'll just write that again up here. A transpose A. Well, in general, I'm going to do the general normal equations. We have A transpose AX equals A transpose Y. We solve for X. Okay. Let's do an example. I'll just take the first one from my worksheet. So we have B is equal to 402. And then we have A equals 1, 2, 0, -1, -2, -1, -3. Okay, and let's find least square solution. Okay, and so it's fairly straightforward. We have all the answers we need. We just solve the normal equations. So let's compute A transpose A, which is a little annoying, but we do it. You notice that when you compute this, this first entry in the top left is just the dot product. In fact, the diagonal elements are just the dot products of each column. Right. So yeah, 4 plus 1 is 5, 2, and 1 plus 4 plus 9 is 14. And then each of these entries are just dot products between pairwise columns, and this matrix you get is going to be symmetric. So it's a good way to check that you did everything correctly. So here we have 2. This needs 2 then. We have -2 minus 2, -4. And then -1 plus 3 is 2. Okay, this is hopefully what we get. And then we just solve the linear system. In this case, we're doing a more general least squares. So we're solving, let's say, x1, x2, x3 equals, and then we can probably compute what a, b is. This one's 0. Then 8 minus 2 is 6. Then minus 6. Let me know if I made any mistakes. And then we just solve this. So since this is section, I will let you solve this. I'm going to let everyone work on this for, oh, you're right. It's a 2 there. It's a typo. Is it? Let's see. 2, 3 should be -1 plus 3 is 2. Yeah, it should be 2. Whatever you get here should be symmetric. I'll let everyone work on this for a little bit. So 6. Maybe a few minutes, and then we'll check our answer. And then we can talk about whatever we want. Oh, shoot, you're right. It is A transpose B. This is incorrect. All right, good catch. Good catch. It's A transpose B. Right here. Okay, let's do that a little more carefully then. 2, 0, 0, 1, -1. I guess even GSIs make mistakes. Okay, this is 4, -2. -8 minus 6 is -14. Great. Which is actually very close to this last column. Huh, interesting, interesting. already we see a solution is 0, 0, -1 is one solution. But maybe there are more solutions, because there could be more than one solution. In fact, these columns linearly independent? That's the question. Or are these columns linearly independent? In fact, I think that's the only solution, if people got that. Maybe someone could confirm that's the only solution. And then there's another part to this problem I put on the worksheet, which is like just compare this to actually orthogonally projecting onto the column space of A. So we can compare this answer if we want to orthogonally projecting on the column space of A. Hopefully I didn't make any mistakes here. Okay, so are there any questions that people have? Anything people would like to do? There's another problem on the worksheet about least squares that we can work on as well, and there's some true false. You just reduce from here, right? Yeah, yep. It's just a linear system that you then solve. In fact, a good way to check this is a times 0, 0, negative 1 is 2, 1, 3. And if this equals the orthogonal projection, then we can check that b minus 2, 1, 3 is orthogonal to columns of A. So something that b minus 2, 1, 3 equals 2, negative 1, negative 1. And just check, take the dot product with each one of these. You should get 0. Hopefully, if you did everything right, if I did everything right, you should get 0. Is there proof for why the row space of a matrix is the orthogonal complement to the null space? Yeah, I mean, we kind of went over that a little last time, which is, I'm going to go to a different board briefly, if that's okay. We're just unwrapping what this means. Your question is essentially the same question as this. You just asked, why is row space of A orthogonal projection equal to the null space of A? And that's just because you can wrap out what this means. So the orthogonal projection of row space of A, so here's A. I'll give myself some more room. Here's A. The row space is the space spanned by the rows. Let's say the rows are A1 through AN. To be orthogonal to the row space, you have to be orthogonal to each row, which means the dot product with each row has to be zero. And so how do you take the dot product of each row? Well, what happens if I multiply this by a vector x? The first entry is exactly the dot product of A1 with x. And so this is equals 0 if x is in row space of A. But this is just the definition of x being in the null space. How did I get this one? So the question is, how did I get this equation? That's because I combined 1 and 2. So 1 says that this vector, y minus projection, is orthogonal to column space of A. And then 2 says that anything orthogonal to the column space is in the null space of A transpose. So this thing is orthogonal to the column space, which means it's in the null space of A transpose. And that's this definition. That A transpose times this vector has to equal 0. Which is exactly the same, I mean, reasoning as why this is true on the right-hand side here. Because A transpose, this is A transpose. Let's say A has columns, I'll say C1 through Cn. Then A transpose has rows, C1 through Cn. And to be orthogonal to the column space, it means that your dot product with all of these columns, C1 through Cn, which are now rows, has to be 0, which means exactly it's in the null space of A transpose. This equals 0 if only if x in column space of A perp. But it's just the definition of being in the null space of a matrix. Okay, so yeah, I think this is the only solution. I didn't actually reproduce it, but these columns, I believe, are linearly independent. Um, let's see, -4 plus 3. Oh, no, they're not. They're not linearly independent, right? You take -2 of this, plus 3 copies of this. Oh, so there should be another solution, actually. Yeah, the rank of A is 2. Yeah, so there should be another solution. When you reproduce this, I guess. Okay, so I'll leave this open now for any questions or problems people want to do. Could we do the true false? Sure. True false. Wonder if I can, no, that's not gonna work. Select. Rather than me writing them all out, maybe you could go to the worksheet. Let's see. A, B, C, D, E, F, G. Okay, so oh, true or false. Let's see if there's a way for me to. All right, well, feel free to shout out some answers. There's another linear regression you can do as well, or least squares you can do on the worksheet. Three A, I'll give you a hint. Should be true. Did anyone get another solution, by the way, for this? I think another solution might be -2, -3, plus +2. Two, -3, 0. Maybe. You got -2, 3, 0 plus x, where x is anything. Yeah, so the question, if there's more than one least square solution, does that mean there are multiple lines of best fit for the data points? It means that, yeah, -2, 3, 1. Yeah, that seems more likely. I guess it means that, yeah, there are, in the previous example, there are two different slopes and b's you can get, and intercepts you can get. But the orthogonal projections are all the same. So you'll notice like these are two different, these are different. But what happens when I plug it into A? By which I mean I multiply A times this. If I multiply A times the first one, I get 2, 1, 3. If I multiply A by the second one, I still get the same vector. And so the y values are the same. So maybe going back to where is it? What I'm saying is that like these might be different. Could be many solutions. But this thing on the right-hand side is always the same. Which means that if you define y1 hat to be m x1 plus b, yn hat to be m xn plus b, where m and b is found using least squares, then these are all going to be unique. Because these are the orthogonal projections. And so, yeah, the line could be different, but the points on the line for each x value is going to be the same. So if you have, so let's look at this picture. Let's draw these a little better. The line could be different, but your hat values these are your hat values. This is like y1 hat, y2 hat. If you just drop every point down, all of these points on the line I'm drawing are all going to be the same. Which I guess means actually the line should be the same. So never mind. Because each of these is unique. I guess for two-dimensional data points, it'll be unique because if you have more than 2 points, 2 points define a line. So you're always going to get a unique line. Since the projection is the same, that means the line is the same. Yeah, it means that, well, let's be a little careful. It means that all these points are the same. So we have to think about it in higher dimensional data. Not necessarily. Maybe we can imagine in this case, in this two-dimensional case, maybe we can imagine the silly example where we're only given one data point. Well, that's a bad example. Maybe in the easy example is maybe like four-dimensional, where you're only given like 3 data points, and then the 3 points are going to be the same, but those won't determine a line. I want to say no, actually. In like very kind of pathological cases. It really just, since the projection is the same, it really just means that the points on these lines are the same. But I guess you can imagine a case in some higher dimensional data where these points don't uniquely determine the line. Anyways, right, it just means that the orthogonal projections are these points. The collection of these points, collection of points is the orthogonal projection. So that's going to be the same. That's unique. Collection of, by points, I mean the y values, I guess, of those points. Because that's y1 hat. Yeah. Yeah, I think so. Yeah, usually we're given enough data points though that once you know all these points, you just know the line itself. But yeah, yes to what you're saying, Hannah. When will the solutions be posted for 15? At some point. Maybe hopefully by Monday or so. I mean, you're always welcome to ask me for solutions like right now. You can go over the true false. So I'll say, thanks for coming. That's all for now. I'll be on any more. I'm also going to stop recording now.